Is it just me or this thing kinda looks like a Christmas tree? Hello strangers, it's me Panic and this is my first and hopefully my last episode of Let's Play Logisim-Evolution. Today we'll be going over my implementation of an 8-bit infix calculator featuring only addition and subtraction that displays the values in base 10. So, without further ado, let's dive right in. After I explain my Christmas tree obsession of course, because from this level of abstraction there are two standard values in this system, 0 and 1. When the two collides, it conflicts. One way to solve this without using logic gates is to use a controlled buffer, but by doing so you're disconnecting the wires from the system, creating a blue-colored undefined state. Here's how the Christmas pull resistor comes into play. It helps with setting the default value to 0, especially when it's undefined. Look at it! Buttons function as you would expect. Not pressing will give 0, pressing will give 1. So, ta-da! Be not afraid, it's not as complicated as you think, especially with my case since I do cut a lot of corners with components in Logisim. First thing first, these are buttons with their value selector. When a button is pressed, the selector selects the corresponding 8-bit value to send down the black data line. It also sends a signal to the one-shot system, which will create a pulse lasting half of a clock cycle from the input signal. The pulse then clocks the register, enabling values to flow in and out of the registers. At the bottom there lies the add and subtract flip-flops, which tracks the state of the operation and controls the output of the ALU, Arithmetic Logic Unit. Since we are only doing addition and subtraction, the ALU features just one lone multiplexer connected to an adder and a subtractor of the two registers, with R1 being the minuend and R2 being the subtrahend in the subtractor. And finally, here lies the 7-segment displays, which will convert our 2's complement from the R2 register to BCD and displays them. This module is responsible for the conversion of 2's complement to BCD, and it inverts our bits and adds 1 to the input if the most significant bit of the input is 1, implying a negative number. It will then send that to an embedded module which will convert our converted unsigned binary to BCD using double-double with add 3 modules. It adds 3 to the 4-bit input if it is greater than or equal to 5. This circuit can be obtained by calculating the Karnaugh maps from the following truth table. Backing out, this 7-segment part also features the 7448, which is just an invert of the 7447. Okay. So, since there are not so much left to be clarified about this part anymore, I'll focus on this instead, the heart of this calculator. There are 2 registers inside this calculator responsible for similar things. The red one is R2, which you can recall outputs to the display. So from now on, I will call this the display. The blue one is R1. It is the minuend in the subtractor. Let's call this the storage. When any number is pressed, the selector of it will send a signal to the gates, which will activate once the pulse from another signal that is sent to the one-shot system is present. It will clock the display, taking in 10Q plus B, with Q being the stored value and B being the button press. Down here is another unit which will do a floor division of Q by 10 when the backspace button is pressed instead of a number. But why these values? Let's discuss it. First being 10Q plus B, suppose you want to enter in 123. You press 1, it multiplies Q by 10, plus 1. You press 2, multiplies Q by 10, plus 2. You press 3, multiplies Q by 10, plus 3. And that is 123, which if we floor divided by 10, we'll get 12. 1, and nothing at all. That's how a backspace works. Moving on from the way it input values, we'll need to talk about the data path. What comes to my mind at first is this: doesn't have any default values. When a number is pressed, it clocks it to display. When an operator is pressed, it clocks from display to storage. Sets the operator and clears display. Pressing 2 equals will take the calculated value from the ALU to display and clear storage. Plus 4 equals, you know the drill. The problem with this design is that it struggles to do multiple operations without pressing the equal sign. My solution is to cut off the connection from display to storage and browse a new connection from the ALU to storage, which activates when any operator is pressed. By default, both registers will have 0 as the default value, with the operator set to addition. When a number is pressed, it clocks it to display, same as before, but now when an operator is pressed, it takes the calculated value to storage. This is the equivalent to moving from display to storage, since adding 0 means nothing. Pressing 2, plus, again, it takes the calculated value which is 3 to storage. 4 equals, Instead of moving to storage, it moves to display and clear storage. Minus. Because minus is an operator, it moves the calculated value 0 plus 7 to storage, sets minus as operator, and clears display. 3. Equals. Same as before, but when pressing equal, apart from just moving, we must also reset the operator to addition for it to be ready for the next session. And that's the data path for my calculator. Surprisingly, I've already explained most of the mechanisms in this part of the calculator. Take a look. Bunch of Christmas trees. Oh, and C, which is clear, clears everything from the registers to the flip-flops, while CE, which is clear entry, only clears the display. Now, for the demonstration, I'm going to set the auto tick frequency to 1 Hz so you can see how everything works, and cue one of my favorite childhood NCS music. Final message. Don't forget to turn the AC up to stay cool.